Have you ever asked yourself why metals are used for electric conductivity while plastics are not? Have you ever known what semiconductors are? If your answer to the previous questions was like a big no, don't worry. Then this video is basically for you. Let's get started. So, the concept of energy bands. Energy bands are basically large numbers of closely spaced energy levels in a crystalline material. The band can be thought of as a collection of the individual energy levels of electrons surrounding each atom. So, for every material, we have a valence band, which is the highest band that has electrons in it. And also we have the conduction band, in which there are no electrons in its states. And between both of the conduction band and the valence band, we have the band gap. Band gap energy controls whether the material will be an insulator like plastic, or a conductor like copper, or a semiconductor like silicon. Now let's consider applying an electric field to different types of materials like a plastic sphere or an electrical copper wire or a silicon chip. The effect of the applied electric field on electrons will be that they will go from the valence band to the conduction band. If this happens, we can consider the material to be good electric conductor. In insulators, we have the following scenario. As the band gap energy between the valence band and the conduction band can be 5 electron volts or more, and that much of energy is not available under normal conditions. So electrons don't move in insulators. In conductors, we have totally different scenario as following. Some electrons are in the conduction band, so it's partially filled, having other adjacent unoccupied states available, so conductors can easily gain energy in response to the applied electric field. Semiconductors have different behavior than that of an insulator or a conductor. Semiconductors have empty conduction bands as insulators, but they have band gap energy that is less than that of an insulator and more than that of a conductor. Now, let's consider the effect of temperature on semiconductors. As the temperature increases, the resistivity decreases, and the population of the conduction band doubles if we increase the temperature by 10 degrees Celsius. Now, let's talk about pure silicon. Pure silicon is not interesting on its own for electric conductivity. That's why we do doping, to be able to get a p-type or an n-type semiconductor. In an n-type semiconductor, we are creating free electrons. We can do that by doping silicon with an antimony. Antimony has 5 valence electrons that connects with the 4 valence electrons of silicon, resulting in a free electrons that behaves like the free electrons of a regular conductor. In a p-type semiconductor, we are interested in holes. We can do that by doping silicon with boron that has 3 valence electrons that connects with the 3 electrons of silicon, creating a hole. The hole behaves like a positive charge. Like a positive charge, holes attract electrons, but when an electron moves into a hole, the electron leaves a new hole at its previous location. That's it, and thanks for watching.